All right, good morning, good afternoon, good evening, everyone, wherever you are. My name is Stan Chung, and today it's my great honor and pleasure to be here to present our most recent research work on extending the bandwidth of 3-5 silicon microring lasers via optical injection locking. And so I'd like to thank all my colleagues listed here for their contributions to this work. So our charter at Hewlett Packard Labs is to re-architect modern computing systems. Shown here on the left is a traditional computing system where information is chopped up to match the limitation of the processor. So essentially the processor is the gatekeeper. Over to the right is our new memory-driven architecture, where we flip the traditional architecture inside out and put the data first, be it dynamic or non-volatile random access memory. We essentially bring the processing power to the data, and what this allows is the ability to ingest, store, and manipulate massive amounts of data sets while simultaneously achieving multiple orders of magnitude less energy per bit. And so the photonics roadmap at HPE is basically aimed at achieving a low latency communications fabric that interconnects all the memory and systems on chip. If anyone's interested, you can visit this link shown on the bottom. And then some people at the company, they've also built this system, and there's actually a YouTube video that shows it. So I would encourage people to take a look at that link. So low cost, high bandwidth density optical interconnects is basically our obvious theme. Our architecture is not limited by a specific form factor. It can enable communication between multiple system on chips, shown by these orange blocks, or inter-rack communication represented by the green boards, or communication between many racks in the data center, shown in this picture below. And then to enable this low latency architecture at HPE, we've developed a comprehensive portfolio of heterogeneously integrated devices on a common silicon platform shown here. And that includes various lasers, high-speed modulators, detectors, passive wake components that involve filters, and also electronic driver chips. So my colleague Di Liang developed a hybrid micro-ring laser shown in this picture, and we've reported both quantum well and quantum dot-based devices via wafer bonding. And shown here is a cross-section where lasing occurs if you place a bias current between the electrodes P1 and N. But the nice thing about this structure is that there's a semiconductor insulating semiconductor capacitor region near the optical mode, where if you apply a voltage between the electrodes P2 and N, you can either operate this device in accumulation or depletion mode, such that you get a really low power phase shifter, and that offers fine tuning of the lasing wavelength. In addition, in collaboration with Texas A&M, shown in this picture down here, we're able to drive an array of these lasers with a custom CMOS driver at 14 gigabit per second, shown here in these eye diagrams. Also here, I've listed some of the current speed limitations of the state-of-the-art hybrid micro-ring lasers. And the bandwidth is typically limited by either differential gain, gain saturation, interband relaxation times, et cetera. But there's always the debate of whether if you improve the modulation bandwidth of each individual device, which is challenging, versus an increased number of lower speed devices in a system. So we've explored several methods to improve the modulation bandwidth of an individual device. And the one we'll be talking about today deals with optical injection locking. So injection locking is quite well known in mechanics, electronics, and optics, but we'll review the basic mechanisms behind it and how we use it to improve the bandwidth of our ring lasers. So we start off with a slave laser, Omega FR1, which is turned on. An external laser called the master laser, shown in this schematic over here, is injected into the system. Slave laser 1 will align itself to the master laser, if we're on the blue side, and it locks within a certain bandwidth, delta omega injection. However, the master laser at the same time reduces the carrier density in slave laser 1, which leads to a redshift of the cavity resonant frequency. And so the frequency offset between the new cavity resonant frequency, omega cavity 1, and the injection frequency gives rise to this beat frequency, which influences the modulation bandwidth. Shown here is kind of a cartoon of what the frequency response might look like. Indeed, we see this in our measurements, which we'll talk about in detail later on. Now, it's also possible that we can cascade slave lasers such that the modulation bandwidth can be extended. And so this is shown here in the schematic, which is very similar to the case before, with the exception that we have a second slave laser implemented on the right. Again, we start with the slave laser 1 that's turned on. An external laser is injected in the system. So slave laser 1, again, will align itself to the master laser with a certain bandwidth. The external laser, again, reduces the carrier density in slave laser 1, which leads to a redshift of the cavity resonant frequency. Now we turn on slave laser 2 and align it closely to cavity resonant omega cavity 1. This in turn injection locks slave laser 2 such that another cavity resonance is redshifted. So this has the effect of increasing energy in the mid frequencies, which can enhance modulation efficiency. And so what you see here in this diagram is that there's additional frequencies in these mid frequency band. So to start things off, we've taken a look at the lasing spectrum of both single ring laser and lasers in an array. For this case, we looked at ring 3 and ring 2 individually. The plot to the left shows the lasing spectrum as a function of wavelength and drive current up to 40 milliamps, and this is measured at 20 degrees C. The free spectral range from each lasing mode is slightly different from each other, but the one here is approximately 3.06 nanometers with about 8 modes observed. Just to note, the ring diameters are 50 microns, which corresponds to the measured FSR. The power of these modes change somewhat as a function of drive current, possibly due to gain alignment. But the micro ring lasers typically have a threshold current of 5 milliamps, although it's kind of hard to see in these plots. The plot on the right shows a similar measurement. Again, the FSR is pretty close, 3.05 nanometers, with the exception that the main lasing peak is kind of shifted over to the right. But kind of observing these two rings allows us to kind of think of having on-chip injection locked micro-ring laser arrays, and we'll show some of those results later on. So just some comments about the measurement system. Cleave single mode SMF28 fibers were used to measure the output. They were angled at 18 degrees. Grating coupler losses were measured to be a high 15 dB per coupler at 1310 nanometers. So there's quite a large spectral mismatch between the lasing wavelength and the grating peak efficiency. And this explains the low powers we saw in the previous slide. And so for evaluating injection locking of the single ring lasers, we used a Santic laser shown in this diagram here. We estimate about like maybe a milliwatt of optical power is actually injected in the bus waveguide of the device. And then we use a PDFA to amplify the signal. And then that's fed into a 90-10 splitter where the 10% goes into an optical spectral analyzer, and the 90% goes into a detector capable of 40 gigahertz bandwidth, and then into a PNA network analyzer. And so the figure on the left shows a small signal frequency response for a free running laser without optical injection locking for different bias currents. It's possible to increase the bandwidth somewhat with increasing bias current, but joule heating starts to dominate, which actually limits the maximum bandwidth to about 4 gigahertz at 16 milliamps. For consistency, we've kept the bias at 16 milliamps to fairly compare the impact of injection locking versus the free running laser. So in this picture right here, the external master laser was turned on. And it was tuned to lock onto various wavelengths. But for the middle wavelength at 1326.168 nanometers, this corresponds to the red curve here. The 3 dB bandwidth is dramatically improved from about 4 gigahertz to 15 gigahertz. And then we looked at various cases where the master laser was tuned plus minus 20 picometers from the center wavelength, and it was observed that bandwidth modulation could be extended up to 23 gigahertz. Next, we decided to evaluate optical injection locking of a single microring laser in an arrayed configuration shown in this inset over here. So we compared the case of with and without injection locking, and we noticed a huge greater than 9x bandwidth improvement, as you can see, up to 45 gigahertz with wavelength locking around 1330 nanometers. So this is noticeably different compared to the single microring laser results shown in the middle picture. And the origins of this bandwidth improvement is still under investigation, but we believe coupled cavity effects could be at play involving gain and loss, and that may have an effect on what some people term PPR or photon-photon resonance, which is a coupled cavity effect. Okay, so the next logical step would be to replace the external master laser shown here with a monolithically integrated tunable high power single wavelength laser. However, at the expense of footprint and power consumption, we instead explored the possibility of using another microring laser to injection lock a secondary microring laser, kind of shown here, ring 3 and ring 2. So for this setup, ring 2 is operated as a master laser, and ring 3 is assumed to be the slave laser with the small signal modulation. So free running operation of ring 3 alone has a 3D bandwidth about 6 gigahertz, as indicated by the blue curve shown here. By adjusting the bias current for ring 2 to these currents shown here, the 3 dB bandwidth can be extended out to 21, 23, 24 gigahertz for these bias currents, which correspond to a certain wavelength bandwidth in the wavelength domain. The plots on the right show the measured optical spectrum and resonant peaks corresponding to the beat frequency between the two lasing modes when both microring lasers are turned on. And so based on this, we're currently exploring the possibility of using ring 1 or ring 4 to enable cascaded injection locking, which we kind of talked about earlier. But the bandwidth with improvement using cascaded injection lock microrings, we can see about like maybe a greater than 4x improvement in bandwidth. So in conclusion, we've demonstrated greater than 9x direct modulation bandwidth up to 45 gigahertz using injection locking. In addition, we looked at the case for using on-chip injection lock microring lasers, excluding the need for external master lasers. And we saw improvement of the bandwidth up to 4x, up to 20 gigahertz. Some things that are currently being explored, we want to look at the unit directionality of an injection locked micro ring laser and see how that affects injection locking. And also we're currently looking at eye diagram quality of injection locking operation. So thank you.